Lab 3, Magnetic Field of Permanent Dipole Magnets. Introduction. So in this lab, we measured the distance dependence of the magnetic field due to a bar magnet. And we did this by applying first a computational model in order to show the different fields acting due to the bar magnet. The main fundamental physical principles we used were the Biot-Savart law, which is the equation given here. And this one is just due to a point charge, but we have the same similar equations for a dipole. And then we use the idea that the magnetic field falls off with the distance. So we have the magnitude of B bar equals K R to the N, where K is just constant and parameters. So in order to do so, we downloaded the magnetometer app, and then we found the magnetometer chip on our cell phone, which is just a figure here to our right. And we did this by using a measuring stick and then the intersection of them, and then we recorded our main observations. So the observations were to find the distance with the x component of magnitude bx equals 20, and then we recorded it as a R20, and we did the same thing for R70, R120, R170, and R220, and we recorded data on the spreadsheet. So here is a screenshot of my spreadsheet where I have R20, R70, and all the other ones on the left, and then their corresponding observations, and then we have the average given, and then at the bottom we also do have the average of everything, and then to the right we have a graph of ln of bx versus ln of r, which I'll explain why there's the ln later, and then that's the equation we ended up with, which is just a simple regression line after some transformations. So the main results are the formulas, and we get after transforming, so taking the natural log of both sides, we get ln of b bar equals ln k plus n ln r. So from the regression model in the previous slide, we know that n equals negative 3.157, and then ln of k is going to be negative 14.971. And we know this information comes from this equation here, which is the regression. And we know that n is going to be our slope, and then ln of k is just going to be the intercept. And with all the information we just found, we can go back and then end up solving for mu. In this case, we got that our mu, or the magnetic dipole moment, is 7.2. However, after some discussion, we realized with the TA, we realized that the value of mu should be negative 2, but this could be due to some discrepancies of our geographic location or some calculation errors or magnetometer recording errors as well. So the main statements that describe the observations are that when the magnetometer is far away, we measure a near zero magnetic field in the x direction, and as we get closer, the magnetometer gets closer to the magnet, the x component increases. So now I move on to the coding part of the lab, and this is a snapshot of what it looks like with all the different electric fields acting on our magnet. And moving on to the actual code, this is what I have. So I have the constant on top, and then I created a cylinder for the magnet, and then we have the dipole B equation, which is just pretty much calculating the magnetic field due to the dipole. And then we just have different observation locations given here, and then we just have the different observations and the arrows created for them. And then we created a perpendicular observation location at an angle of 45 degrees. So we compare the experimental findings versus the B-Python model. However, we used a slightly different distance. So the D experimental was 0.24371 meters, and the D model is 0.243669 meters. It's slightly different, not that much. However, we do get different resulting magnetic fields, where B experimental is just going to be negative 0.000268, negative 0.00043, and then negative 0.00044 Teslas. And then our B for the model is it's slightly different. It's 5.443 e to the negative 6, 1.633 e to the negative 5, and then 0. And while there's a difference, it's not very concerning as all the values are very close to 0. And the difference might be either because there's a different distance, or some human error, and then we could have gotten the wrong magnetometer measurement, which could have led to a different magnetic field. So for the first question, if we hadn't taken the magnetic north into account, the experimental values would not have been accurate, as a magnetometer would have considered the magnetic field of the Earth and the one of the magnet. So rather than getting B magnet only, we would have gotten the result to be just a combination of the magnetic field of multiple sources. So if we were to stick two identical magnets end to end together, the magnetic field would just be added up, and then we would get that the magnetic field of two magnets would be greater than the one of one magnet, and it would be close to twice as strong.